we have a very long-lasting collaboration. So Rafael is not only a very good colleague, but I would also say a very good friend over the many years of collaboration. So more than 20 years, so I think it's appropriate to say that we are friends. And Rafael was also one of the people working on hybrid AI, and normally, I guess you would not associate fuzzy systems with hybrid AI, but for me, it's really an example of combining symbolic reasoning with numerical representations. And today, it's like hybrid AI is something new, but we have been working on this already for many years. But today, you're going to talk about explainability, right? It's in the context of trustworthy AI. But before I give you the word, I also want to say that Rafael Bello won a lot of awards, also together with his team. It would take too much time to enumerate all of them, but maybe a recent one I want to mention is the TWASP one, and the one as an international recognition by UNESCO for all the work you have been doing in the field. So I think that's a very nice recognition. And with this, I will give you the word for your presentation. We are looking forward to it.
Thank you, Anne. Good afternoon. First of all, I want to thank to BrIAS for this possibility to develop this research training here and collaborate with other colleagues, especially to Professor Anne that she invited me to apply for this grant. Also, thank you very much to participate in this activity. I will present some consideration about that work that we developed related to explainable AI. And said, I am from Universidad Central Marta Abreu de las Villas. This university is in Santa Clara, a city in the center of the island. Here. About 280 kilometers from Havana, that is the capital of Cuba. The presentation includes three main points, some elements about the AI, the result that we have developed at UCLV, and other tasks on the development at this moment. Mainly, we'll focus about the relation between the rough set theory and the possibility to build counterfactual explanations. As you know, there are several definitions about what is AI, and for that reason, some authors prefer to talk about AI systems. That is the definition that the European Union gave about AI system. Here I want to remark some main elements that this AI system perceiving their environment, acquiring data, interpreting them, in order to decide to achieve a given objective. In order to develop these AI systems, the main component is the knowledge in the domain. There are different sources for obtaining this knowledge. In the first stage of the AI, the main sources were the experts, and after that, the structured data and non-structured data were used in order to obtain the knowledge using machine learning techniques. There are many and different sources of informations, different encoding systems and applications that we use daily. And in fact, in this moment, the AI systems are in everywhere. You can find intelligent systems related to robotics in different home applications, in different computational systems, and of course, in all the decision support system. The problem is that related with this application, there are some problems because possible error may be have a high risk for the human in general. In applying AI in the society, there are several possible problems. Among them, adaptive learning is costly and time-consuming to build. The algorithms can be a black box, and there are also problems with security and trust issues. For that reason, there are new terms related to AI. This moment we can talk about responsible AI and AI safety. In order to increase the credibility of the AI, there are many aspects to take into account, such as fairness, robustness, lineage, and explainability. In the first case, the system must be free of bias to avoid unfair treatment for certain groups. In the case of robustness, the system should be safe and secure. In the case of lineage, the system must include some elements in order to guarantee the auditability. And in the case of explainability, not only is necessary to provide the decision, but also the reason for obtaining that solution. In this aspect, I will focus the presentation. So we will talk about this new field, explainable AI. In general, we can talk about two types of machine learning methods, whiteboard and blackboard. Some machine learning methods, such as linear regression, logistic regression, and decision trees, are trampolines. The system allows to obtain a solution, but also it's possible to understand the process by which this solution was obtained. That is the type of whiteboard methods. But there are other type of algorithms, such as support vector machines and different type of neural networks, that is impossible to understand what is the reasoning developed by the system. This is the case of blackboard systems. This is an example of a whiteboard. In this case, one decision tree. In this case, the intelligent system could predict pass or fail, but in any case, you can follow one branch on the tree in order to know the reason for the prediction. But in this other case, the system uses a neural network, and it's not possible to understand the element that compose the model in order to understand the reasoning. So, at this moment, we can talk about two types of AI, the classical AI and the edge AI. In the first case, we have the classical model. We can train the model by using some learning process, and after that to use it in order to solve problems. But there are many questions that is not possible to answer about the solution. The purpose of the AI is to obtain the solution, but also can answer that question. But related with the AI, there are some problems. There are different definitions about what is an explanation. There are different stakeholders with different interests. For instance, we have experts of the domain, about AI expert, lay user, etc. There are several questions to answer: how, why not, what if. And there are different forms to express the explanation. We can use the relevance of the input, but also we can use example prototypes, tests, or counterfactuals. And other important aspect in this field is the evaluation, in order to determine the quality of the explanation. This is an example of the explanation. In this case, we use the method LIME. In the left part of the slide, you can see the relevance of several inputs, and in the case of the right, you can see the text in which some words are pointed out, indicating the relevance to the prediction. In the case of image, the result is to point out some pixel that inside in the prediction. There are several AI methods, line, LRP, sensitive analysis, anchors, LOR, CHOP, etc. These methods can be organized in different ways. For instance, global and local, agnostic and agnostic, according to the input that the method used in order to generate the explanation, and also take into account the form in which the explanation is expressed. After this short introduction to AI, I will talk about some research that we have developed in our AI lab at UCLV. In order to develop this application, we have formulated one approach. This approach is based in three considerations: to whom the explanations are addressed, also that the explanatory capacity of the intelligent system must evolve as the system developed. It's not the same in the first stage of the system that in the final stage, and also what information is used by the methods in order to generate the explanation. According to that, we have proposed three types of application. The first type is we call algorithm explainability. The second, domain-based explainability. And in the third case, we talk about human-centered explainable AI. And our applications follow these different types. The first type is more powerful for the AI expert, and usually is the case to generate the explanation in the first state of the intelligent system. In the second type, the domain experts are more involved because we need the knowledge about the domain and their criteria. And in the last type, all stakeholders could be involved because the explanation is developed using an interactive process. This is main element of the type 1. In this case, the methods use the learned model, the input, and the output, that is the prediction of the system. Several methods developed in AI are used in this first type: line, LRP, LOR, CHOP, etc. And usually the output of this type are the relevance of the feature, but also maybe heat maps or factual or counterfactual rules. In the case of the second type, we use also the domain knowledge. The purpose of this is to increase explanation with semantic information by introducing vocabulary and terminology of the domain. In order to introduce this domain knowledge, we can use user models, prototypes, ontologies, and knowledge graph. In the case of the type 3 explanation, we call that this human-centered explainable capacity. In this case, the human have the main role in the process to generate the explanation. By means of the interaction between the humans and the stakeholder and the system, we can follow two alternatives: asking user to provide explanation, and the system can learn how humans explain, but also use to interactive interface in order to freely explore the space of possible explanation. There are some examples that we have developed using this approach. The first example is this: one intelligent system in order to predict coefficients related to COVID. For this problem, we use clinical studies that have shown that factors that increase the lethality of the COVID are the presence of co-infections. And in general, we can identify two types of co-infection, bacterial and fungal. The purpose is to giving the data of patient to predict the possible co-infections. This problem was modeled as a multi-level classification. We used several patients from different hospitals in Cuba, and these patients were described using 98 attributes. distributed in 5 types of attributes. Of course, the decision feature was the no confusion or the type of confusion presented. The solution includes 2 main elements, a multi-level neural networks, and this AI methods, LRP, but we have to develop some alternative in order to adapt this method for the case of multi-level scenario. This is an example of explanation. Here you can see the relevance of each feature. The color indicate the degree of importance in order to the prediction. A second example is the prediction of the generation of a photovoltaic park. In this case, the input are time series, and we use 2 models in order to solve the problem. 2 types of deep neural networks, in this case, convolutional networks and low short-term memories. The problem is to predict the generation of a park 24 hours forward. And we include 2 AI methods, in this case, LIME and CHAP. This is an example of the explanation using LIME, similar using CHAP. In both cases, you can see that the feature variance is the most important in order to predict the generation of the park. A third example is related to the opinion mining applied in theories. For this problem, we have a set of opinion about Cuban hotel from several websites, and we use 2 models to the prediction, Bert and Roberta, and different methods in order to generate the explanation. This is an explanation using LIME. You can see the relevance of each word in the opinion. This is other 4 in order to present the explanation. And this also, you can see clearly the relevance of the word in the opinion. This is one example related to the type 2. In this case, the problem is to predicting deaths in an intensive care unit. For this, we use the patient in the intensive care unit in the hospital Hernando Milian in Santa Clara. Those patients were described using several attributes between them, age, hypertension, Apache 2 scale, soft scale, etc. But moreover, we use several domain knowledge related to this problem. We use a knowledge graph based in different ontologies. This knowledge graph include data about the patient, the diagnostic therapy, and other things, and several ontologies related to the descriptor and vocabulary used in this problem. The AI system includes 3 main components: a prediction model, 1 module to construction a basic explanation, and a third model include in order to refine the explanation. So, in order to predict the did or not did, we use a neural network, but also 1 rule-based systems. Using the information in the rules and in the ontologies and knowledge graph, we can construct one first explanation, and this explanation is refinement using 1 large long model. So we have here 4 steps: prediction using the multi-level percentron, made the prediction using a set of rules. In this case, we have 93 rules related with the problem, using the rules and the knowledge graph in order to obtain a first explanation, and using the information in the knowledge graph and the LLM, we can obtain a second version of the explanation, in this case, in natural language. The other result is a meta explanation. Taking into account there are diverse stakeholders and different interests and there are many AI methods. Identifying the most appropriate application can be challenging, and our proposal is to use a multimodal perspective in order to generate the explanation. The idea of the meta-explainer is similar to the concept of the meta-classifier. In this case, the meta-explainer integrates the result of multiple basic AI methods in order to obtain one explanation with higher quality. The process includes 5 steps: generation, grouping, evaluation, aggregation, and visualization. First, several explanations are generated using several different methods. These explanations are clustered according to the type of the explanation. The explanation in each cluster is evaluated, and after that, the explanation in each group is combined using different aggregation operators. After that, we have one explanation for each type. This is a graphical representation of the problem. We obtain several explanations and cluster them, and after that, we do the evaluation, the aggregation, and finally to present the meta-explanation. At this moment, this meta-explanation includes 2 types of explanation: relevance-based explanation and counterfactual explanation. In the case of the relevance-based, we use this measure, LSE estimator, in order to evaluate the explanation, and use 3 operators in order to aggregate the explanation: weighting, union, and intersection. In the case of counterfactual, several properties are used: proximity, sparsity, etc. And in this case, the aggregation is performed using 3 elements: the scoring, the explanation, ranking this, and aggregate this ranking. The other task is related with counterfactual explanations. Counterfactual explains hypothetical alternative situation in which a desired outcome is predicted to occur. A counterfactual explanation is a prediction describe the smallest change to the feature values that changes the prediction to a predefined output. Usually, the methods to generate counterfactual are agnostic, and in general, they produce a new instance. This is an example. Suppose we have this intelligent system in which the purpose is to predict to accept or not a credit application. In this case, suppose we have this information. The first row indicates the input, and this application from both was not approved. But the row 2, 3, 4, and 5 indicate possible counterfactual information. You can see there are some values in the input that with other values. But in the case of the last counterfactual proposal, it's not possible because it proposed to decrease the age of the applicant. So there are different problems related with the generation of counterfactual problem that we will talk about this. In general, there are many advantages of using counterfactuals, because counterfactuals are intuitive nature. It's easy for no expert to understand. Other important element that the counterfactual focus on actionable insights in order to change the output, and also usually the counterfactual alignment with decision-making process. Moreover, counterfactual helps identify discriminatory behavior and promote fairness, can be generated using different models, and this can reduce frustration and feeling of unfairness. But there are also some limitations. Finding optimal counterfactual can be computationally costly, and if we can obtain several counterfactuals for one problem, maybe there are some ambiguity in this set. But independent of this, the agree of many authors is that the counterfactual are especially effective for human-centric and practical applications. In order to evaluate the counterfactual, we can use different properties and metrics. For example, validity, similarity, sparsity, actionability, plausibility, robustness, the quantity of the counterfactual that we can generate, and also the cost to obtain this counterfactual. There are different methods, and one classification of these methods is this. In this case, we can identify 4 group methods: optimization-based methods, model agnostic sampling methods, prototype-based methods, and hybrid approach. This is a list of different methods to obtain counterfactual, certified, lower, maze, clear, and etc. For instance, in the case of the methods lower, we use this in order to explain the problem of coefficient that I previously explained. In this case, this method produces 2 rules, one factual rule and other counterfactual rule. Remember, this is the explication that we obtained for that problem using line, LRP, and this is the explanation that we obtained using LOR. This is the rule, the factual rule, and this is the counterfactual rule. The first is the case of a patient with no coefficient, and the second is the case of one patient with coefficients. So the explanation includes these 2 types of rule. Other important problem related with counterfactual is if the counterfactual is realistic or not. Infeasible counterfactual are those that suggest changes to input that are unrealistic. For instance, to decrease the age of one person in order to change the solution. The problem with this type of counterfactual is these counterfactual affect the usefulness and the credibility of the explanation. There are different reasons for that. The method can be obtain different infeasible counterfactual. For instance, maybe the methods do not use the domain constraints. The method can be prioritized, minimizing the distance between the input and the counterfactual, considering whether the subject changes are realistic or not, and also the counterfactual are outside the training data distribution. In order to solve this problem, one idea is to use out-of-distribution technique, that is combine the out-of-distribution technique with the method to generate the counterfactual. This can perform using different alternatives, estimate the probability density of the training data, and reject counterfactual with low density, train an autoencoder, use generative model like variational autoencoder, train a binary classifier to distinguish between in and out distributions examples, and measure the distance between the counterfactual and the nearest training data. But here it's important to take into account that the of distribution technique assume that the training data distribution represent the real world distribution, which is not always be true in some applications. We have formulated some ideas in order to use the learning of the rough set theory in order to improve the quality of the counterfactual. Usually, the counterfactual methods are divided in two classes: blind perturbation and experience guide. We are focused in the second type of method, that is experience guide methods. Our proposal includes 2 ideas: using information from the rough set theory to improve the generation of the counterfactual, and that some properties about the counterfactual generation could be evaluated depending on the region of the input. We can formulate different questions related to this proposal in order to guide the research. I will focus on two important properties, plausibility and robustness. The plausibility of the counterfactual is related that a counterfactual is plausibility if the could be a valid point in the domain. That is some requirement. Given a reference population X, a counterfactual is plausible if feature values in the counterfactual are coherent with those elements in the population. The generative counterfactual should be located in the feature space of the data. Remember, this concept is related with other topics such as out distribution, data manifold, and data probability distribution. Also, a plausible counterfactual should not be labeled as outlier. Some authors thought about plausibility and feasibility in the same way, but others established some difference between these two terms. One important metric in order to estimate the plausibility of the counterfactual is the local outlier factor. Many papers use this metric in order to evaluate this property. Our ideas in order to improve the plausibility of the counterfactual using robustness theory include to consider three main concepts of this theory: the lower and upper approximation, and the concept of unreduced. We have formulated these three hypotheses. Generate counterfactual within the lower approximation to assure high confidence, or maybe use element in the upper approximation but accept some uncertainty. A second idea is generate counterfactual by modifying only the feature in the reduced, could reduce complexity and ensure change are meaningful. And the last idea is that the raw membership value of the counterfactual could be used to assess how well it fits within the desired class, and reject counterfactual with low membership values. The other property is the robustness. Counterfactual explanation should be valid for all individuals similar to the input. That is a formal definition of this concept of robustness. In this case, the goal is to design a counterfactual explainer that guarantees that whenever two inputs are close, there the corresponding counterfactual also are close. This property is related with other terms in this field, such as sensitivity and stability. But there are several studies related with the robustness in the field of counterfactual. Most of them have shown that the majority of popular counterfactual explanation methods are not robust, and this is a problem. Usually, the analysis of robustness fall in three categories: robustness to input perturbation, robustness to the model change, and robustness to a parameter of the AI methods. At this moment, we are focused in the first category. Other studies have shown that irrelevant features do not affect the robustness, highlight the connection between the robustness of the counterfactual explanation and the predictive importance of the features, that generating robust counterfactual is especially challenging for data with many features with high predictive importance, and few features with high importance favors obtain robust counterfactual. This all result is useful in order to formulate our ideas of using robustness theory to improve the quality of the counterfactual. Other studies show that whenever an input is between two decision boundaries on opposite sides, a minor change in the input can result in a major change in the counterfactual, and others show that examples close to the classified decision boundary do not provide a robust counterfactual. Taking into account this result, we have formulated some questions in order to guide the research. Using features in the reduced or core may increase the quality of this property. Using the result measure to weight in the feature could improve the robustness. Is there a relation between the size of reduced and the robustness? Using feature in the reduced or core could relate robustness and sparsity. And this establishes that if the input belongs to the boundary of the class, maybe the robustness is lower. In order to develop this task, we have implement a framework. This framework includes same main elements. We have selected some methods to generate counterfactual. Also, we have selected a set of data sets used by other authors in order to generate counterfactual. And also, we have selected a measure for evaluate robustness and plausibility because there are different methods for estimate that measures. After that, a model is built for each data set using a multi-area percentile. Counterfactual are generated using the selected methods, and the robustness and plausibility are calculated by using the metric that we have selected in the third state. Using this information, the question is how to improve this result using the rough set theory. Finally, I want to talk about some element of the rough set theory. This theory was developed by Paulak in Poland in the early of 1980s. The rough set theory includes two main components, the information system and one indecibility relation. This is an example of the decision system. You can see here the universe includes 7 objects, and each object described using 3 attributes. Maybe if we consider what as a decision attribute, we can say that this is decision system. The indecibility relation usually is one equivalent relation with this property, but also there are some extensions of the theory using similar relations. Using this relation, we can obtain different granulation of the universe. For that reason, the rough set theory is a main component of the granular computing. Here you can see there are different combinations of the attributes, and each combination generates different partition of the universe. Here the main concept of the theory, the concept of lower and upper approximation. In this case, this is the concept of lower approximation. It is a set associated to a class that includes instances that definitely belongs to the class. And in the case of the upper approximation, this set includes instances that might belong to the class. This is the main concept of the theory, and using this we can calculate the boundary of each class. We said that one set is rough if the boundary region is not empty. This is the representation of the different concepts, the set, the lower approximation, the frontal, the boundary, etc. The other important concept is the concept of reduced and core. In general, a subset B is called a reduced. We can obtain using this feature the same granulation that using all features. That is, reduced is a minimal subset of features required to preserve the classification. And the core is the intersection of all reduced. The upper-lower approximation, the boundary, and these two concepts, reduced and core, are the most important element of the rough set theory, and is the element that we use in order to study the behavior of the counterfactual methods. So the idea is that using the rough set theory combined with the different methods to generate counterfactual, maybe the property can be improved, plausibility, robustness, sparsity, etc. Thanks very much.
Thank you. Questions? Maybe I'll start with a question. At some point you also mentioned domain knowledge, knowledge graphs. I think it was on the slides. How do you see this combined with the rough set approach that you take? Or would that be hard to do? Because so you also mentioned it has an impact to whom you explain something, which is of course true. So how can you include that in the framework?
But in this case, we have used the domain knowledge in order to generate factual rules, no counterfactual rules.
Okay.
And the idea of the rough set that we are developing is related to improve the quality of the counterfactual.
Yeah.
But maybe it's possible to use the graph knowledge in order to express the counterfactual rules as in natural language.
Okay.
It's possible.
And are there links between rough set theory and knowledge graphs, or?
There are some links between these two because using knowledge graphs, we can establish relation between the element of the information system.
Yeah.
And for instance, in order to estimate the similarity relation, it's useful if you know the relation between different terms in the domain.
Mm-hmm. Okay, yeah, thank you. Other questions?
Hi, thank you for the presentation. So this, I'm not familiar with RST, so it can somehow describe a data set. So that is can it be used to describe a data set and find these partitions?
Mm-hmm.
Can it be viewed as a source or as a method to explain the data set, the training data set? Is this?
In all of this example, excuse me, for instance, in the first example, this is tabular data. There are, in this case, we have about, in the case of confusion, about 2,000 cases described using these 98 features. That is the type of data that we use. In the case of the photovoltaic park, the data are time series, with different elements. In the case of opinion, the data are text. So the problem is to classify this text.
Yeah, but maybe you can repeat the question.
Right. So I was asking about the rough set theory.
Uh-huh.
If you can apply to what kind of data, and what would be the things you get out of this?
Okay.
If it can be used for explaining the data.
In the case of rough set theory, the classical version of the theory is formulated for tabular data. But there are some applications, for instance, in the case of image, because we convert an image in a vector of pixels and find the relation between the pixels. But usually is adapted to the case of tabular data.
Okay, and the second part of my question, can you see RST, the rough set theory, as a method for explainability itself, to explain data? Could it be used for explainability alone, without integrating with counterfactuals?
I believe not. I believe there is possible to obtain some good properties of the explanation using the idea of rough set, but no use directly the concept of rough set in order to generate the explanation.
Okay. Thank you.
In the case of images, how would it relate to, for example, a heat map? Is there some similarities? Yeah.
In fact, there are some work related with this question, because, for instance, the concept of reduce. The reduce is the most important feature in order to obtain the classification, in the case of classifications. And a heat map indicates the most important pixels
Yes.
in order to make the prediction. So the idea is that there are relation between the reduced and heat map. For that reason, our idea is that if you use the information of the reduced, you can improve the quality of the heat map, because we can decrease the composition cost in order to not analyze all image, not only focus for some part.
But maybe to come back to the previous question, knowing that you also did work on like finding prototypes, I think it's also based on the rough set theory that you find prototypes. So if you go via that path, I would say it can somehow be also a method to improve explainability of the data on its own without the counterfactual part.
In fact, we have developed one method in order to generate prototype using the concept of the rough set. In that sense, it's possible to use the prototype as
finding prototypes in your data set, I would say that this can also be giving insights. So it's maybe not a classical explainability, but it helps to understand the data, I would say. Other questions? No? In this case, let's thank the speaker again, and we'll have a coffee break.
Thank you very much.